recording. Let me make sure I do that. Okay, now we're recording. So we're talking about adhesives, and one of the advantage of adhesives is there. Oops. That's still not doing what I want. Maybe this is it. No. One of the advantages of adhesives is being able to bond thin sheet materials. So if you have two pieces of wood or two pieces of veneer, something like that, can you all see that okay? What I'm drawing?
Yeah, so far it's just two lines, but we can see it as you're drawing it.
Okay, it's big enough and all, dark enough and all that. So, and you have glue in between. That's where glue works the best. But if you have a situation where you want to, for example, glue a 2x4 to a joist or a header or something like that, now using glue doesn't make a whole lot of sense. The reason for this is because the bond strength of glue or adhesives per unit area is much, much smaller than mechanical fasteners, like a nail or a bolt, right? So if you have a nail, you're nailing into the end grain, so you don't want to do that. But just for examples, the mechanical strength that you can get here with a mechanical fastener is much, much greater than you can get with glue. So the thing that you need to be aware of when you're using adhesives is you need surface area, right? And this is going to come up again because it's a very important, the whole idea of surfaces and surface area and adhesion is what we're going to be talking about today for the most part. So that's one advantage or disadvantage of adhesives. And, man, this is slow. But you also have, because you have a large surface area, you can often see improved stress distributions, right? Because the bond is over a larger area. So you have the stress is distributed. You can also have dynamic fatigue resistance because the glue oftentimes will bend. It will be more, but not as rigid as a nail or a screw or a bolt. And therefore your fatigue resistance is higher because it can bend as the substrates bend, right? Whatever you've got it glued together. So it can be low cost. You can have automated application. And it also gives you a lot of design flexibility that you can't get with mechanical fasteners. Like if you wanted to join two pieces of veneer using staples or nails or screws or bolts, would really limit you, right? Would really limit you. And also with glues, you can glue paper together, for example, and make a honeycomb type of structure. And those are used in a variety of places. They're used on boats. They actually flew on the space shuttle. A honeycomb structure made out of paper and glued together was one of the, I don't know where it was in the space shuttle, but it was somewhere in the space shuttle. It's lightweight and strong for the weight. No visible attachments, right? You can have improvement in corrosion resistance. The glue's not going to rust. It can be lighter weight than mechanical fasteners. And not usually it is, right? And the other thing is, but you're putting it on the surface, so it's if you have a good adhesive bond, you've also have a seal on the surface, so the surface is sealed, so you can join and seal simultaneously. And if you're trying to compare it to nails or screws or bolts, where you're putting some, where you can put, especially with nails, put shock on it, then the glue avoids that. And lack of stress concentrations is another one that, so you engineers need to stop sharing. Can, oh geez, can appreciate, I hope. So if you have a substrate like this with a hole in it and you pull on it this way, which way does it break? So let's see, who's an engineer here? Annabelle, you're an engineer. Which way is it going to break if you're in this situation?
Would it not split at the fastener?
I'm sorry, I couldn't hear that.
Would it not split at the fastener?
I don't know what's wrong with your audio, but it's not coming across clearly. Is it going to break this way or some other direction?
Can you guys hear me now? I'm sorry. I'm having some troubles with my microphone.
Okay, that sounds better, yeah.
Okay. Would it not split at the fastener?
I'm still not getting it. Okay. So when you pull this way, when you have a defect and your stress is in this direction, the stress concentrations go like this, right? So your highest stress is actually in this direction, and it'll break in that direction. So when you have so if you're using a nail or a screw or a bolt, you're actually putting defects into your substrate, whatever you're putting it into. If you use adhesives, then you can avoid that. Okay, so this is definitely slow way to go. All right, disadvantages. So as I mentioned before, the strength of your overall bond depends on the surface area and the quality of the bond, right? If you've got two dusty, dirty, covered with sawdust pieces of lumber, you can nail them together or screw them or bolt them, no problem, doesn't really matter. With glue, it needs to be, as I'm sure everyone knows, clean and dry, right? And a big problem with glue is there's very much a lack of non-destructive quality control methods. Now there are some, right? You can, it's based on what they call it. You can do testing as long as you can bend it, and they do this in, like for example, plywood mill. You can bend it, and as long as you stay in the elastic region, you can bend it and you can get a number for stiffness, and then that'll be non-destructive. So there are some ways, but for strength, you just have to break it, right? And of course, while it can be cheaper, it can also be more expensive than mechanical fasteners. And another important limitation of adhesives, not so much for us, but for adhesives in general, is because they're organic compounds for the most part, their upper surface temperature is limited. And for most adhesives, the upper surface temperature is somewhere around 200 degrees C, and that just happens to be the upper temperature we want to use with wood. So there's a reason for that, because most of the glues or adhesives are organic polymers, and wood is an organic polymer. So they both have similar temperature behavior. Now, there are adhesives that will go to higher temperatures, and there are plenty of adhesives that have a lower surface temperature limit. But in general, it's about the same as wood. So it's not really a problem for us, but it can be a serious problem, for example, in aerospace or automotive, places like that. So I think I already covered this. This is basically talking about surface area. So the bonded area has to be large, or you want to use a mechanical fastener. Or you want it in compression, where all it has to do is just keep it from shearing sideways, and that can sometimes be accomplished with adhesives. So when I first started developing this lecture, I was looking for definitions of adhesive and adhesion. And if you look in the dictionary or online, it's not very helpful, because it will say an adhesive is something that causes adhesion. And if you look up adhesion, it'll say what adhesives do. So it's a kind of a circular thing. It doesn't really help very much. But I finally found these in a physical chemistry textbook. So it talks about the adhesive being a material, bonding and holding. Adherence is a little lingo word. It means just the two things that you're gluing together. Salt adherent or substrate mean the same thing, right? Synonyms. And but it means by surface attachment, right? So this surface attachment is important when you're talking about adhesives. And adhesion is a molecular force across a surface of contact between unlike liquids or solids, or like liquids and solids that are just two different pieces, right? And we're not going to trouble ourselves with liquids, but solids that resist interfacial separation. So you have two pieces that are glued together, and what adhesion is resistance to separating those two things that are glued together, right? So that's what adhesion is. And the adhesive is whatever you're using that works to give you resistance. And the more resistance you get, the better the adhesive. Okay. So, and then the lingo here, as I mentioned, so this is, I guess I could do this. You have an adhesive assembly, which is the two substrates or the two adherents, and the adhesive joint with the adhesive in the middle. So you have two different things you're gluing together, and the adhesive in the middle. That whole thing can be called an adhesive assembly. And then you have the adhesive joint, which is the surface areas or the interfaces here that are bonded together. So, unfortunately, there is no one theory that can explain all different types of adhesion and all different types of glue and how they work. So typically there are, if you look in the textbooks, they will tell you about 5 different theories or mechanisms that describe the different types of adhesion that can take place. So let's go over those. First one we'll cover is the diffusion theory. So this one is, a best example of this one is PVC pipe. Hopefully everyone has glued PVC pipe together or seen it glued together at some point in your life. And as it shows in the picture here, you take here it's primer, right? You're taking that purple primer and taking it out of the bottle. It's a liquid, and you spread it on the surface. Put on the primer, you put on the adhesive, and then you jam them together and you get the adhesive assembly or the adhesive joint. and it works really well. And the way it works is the primer is a solvent for PVC. PVC is polyvinyl chloride. It's a polymer, and it dissolves in a variety of solvents, and it dissolves in the solvent that's in the primer. You also have solvent in the glue. Also in the glue, you also have some PVC itself, right? So when you apply the solvent, the primer and the glue, you're applying solvent and more PVC. So when you put those two things together, the reason it smells is because the solvent has a high vapor pressure. So when you jam these two things together to make your adhesive assembly, the solvent's evaporating fairly quickly. And what that does is while you have the solvent connecting those two pieces, the PVC that's in the glue and the PVC that's in the two pieces are diffusing, and they're diffusing together. So then when the solvent evaporates, there's nothing left but polymer. So you just have solid polymer making the bond. It works really well. As you know, if you glue two pieces of PVC together, don't try to separate the bond, right? It's not going to break at the adhesive interface. You're done. You can cut it out and put in a new piece or whatever. So the diffusion theory works really well, but we don't have any solvents. We can't really do this with wood. There are some things that dissolve wood, but they don't have high vapor pressure. They're expensive, toxic, difficult to work with. So this sort of thing is not done with wood, but it is one of the 5 theories of adhesion. And here's, I forgot about a cartoon. The next one is the electronic theory. So this one says you have negative and positive charges. Maybe duct tape works with this mechanism, although this entire mechanism is in disrepute, because of an incorrect assumption. There was a famous adhesives researcher, professor, that came up with this theory, and then when people tried to duplicate his results, because he published papers and had data and all that stuff, when people tried to duplicate his results, they couldn't. And what he did was he forgot that when you try to break this adhesive joint, then you're pulling, like you'd be pulling this way and this way. Maybe some of you have done internal bond experiments on wood adhesives. So when you're pulling this way and this way, what he forgot was you're also pulling on the substrate and it's bending. So you have some energy that's absorbed by the substrate itself. And he didn't account for that. He assumed all the energy came from these electric particles. And doesn't work that way, right? So this theory is pretty much disrepute. But it still gets listed in the textbook. The third one is mechanical interlocking. And this is physical entanglement of two different materials. And so you have resistance to separation from physical contact. One example of this is a zipper, right? Close together. That works pretty well, and it's a mechanical interlock. And because wood is a porous material, it also has mechanical interlocking is an important part of the bond strength in wood adhesion, right? So you need for the adhesive to penetrate into the wood to make a good bond with wood adhesives. Generally, the rule of thumb is you want to go about 3 cells deep. If you go deeper than that, you get diminishing returns and you're wasting money. But if you don't go that deep, then you don't get as good a bond. It kind of is optimized around 3 cells, something more like that. Of course, that's very difficult to control, but that's kind of the idea, right? The mechanical interlocking is not the whole story. And so mechanical interlocking then, another good example of mechanical interlocking is Velcro. And so you can see here, Velcro, hopefully everybody knows how Velcro works. You have hooks and loops, right? So you got loops up here and hooks of plastic down here. And you can see here that you have, once you get them together, this is a different kind of Velcro made a different way. They just break, they make thick loops and break them to make the hooks, right? But you can see that the once you press it together, then you can get the hoops through the hooks, and that gives you mechanical interlock. Okay. If you got any questions, just ask, right? Please. Okay, number 4. This one we chemists really like because for this one, we want covalent bonding between the two substrates or adherents. And to do this, it makes sense. It makes intuitive sense that if you have a compound, an adhesive, that chemically reacts with the surface you put it on and forms, for example, a carbon-carbon bond, very strong bond, and it does that on the other surface too, then that has to be intuitively, you would think that that has to give you the best possible adhesion. Turns out that's not really true. And because of theory number 5, which we're going to get to. So but there's been a lot of research done on this, on chemically modifying wood and adhesives. It's fun for us chemists because wood is actually easy to modify chemically. And so it's easy to play around with it in the lab and come up with lots of different ideas that at least somebody thinks is clever, right? In terms of the 3 major wood preservatives, which are urea formaldehyde, phenol formaldehyde, and isocyanate glues, and hopefully everybody's familiar with that. The isocyanates have the ability to bond to wood hydroxyls. So there has been some debate in the literature, or discussion at least, about how much this bonding of isocyanates to wood hydroxyls contributes to the bond strength of isocyanates, because isocyanates are an excellent adhesive for wood. So there's no, I think the general consensus today is that while, yes, this is possible, yes, it does happen, it's not the major source of the adhesive bond strength in isocyanate glues. However, what it does do is by bonding to wood hydroxyls, it then prevents those hydroxyls from participating in hydrogen bonding when the wood gets wet. So in terms of, or even when you change relative humidity and the moisture content comes in, right? So the isocyanate can contribute probably more to durability of the bond than it does to strength of the bond. Okay. So the 5th theory is the big one. This is called the adsorption theory. And adsorption adsorption means it's from the Latin, and ad means on, and ab means in, right? So adsorption is about things being on the surface, not in the surface. Absorption is about things being absorbing into the wood. And so the van der Waals or the adsorption theory depends upon molecular forces. So remember in our definition, it talked about the molecular forces on the surface, right? So we're talking about surfaces, and we're talking about the molecular forces between the adhesive and the wood substrate, or any kind of substrate for that matter. And we're talking about van der Waals bonds. So what are van der Waals bonds? So we have, if you think of it, I'm going to draw a simple Bohr model atom, right? Even totally simplified. So if you have, when you have an atom, you have a nucleus that's positive, right? And you have an electron that runs around in an orbit around the nucleus. That's the structure of an atom, okay? Now, if you think of this electron as a particle running around and circling around an orbit, like the Earth goes around the sun, that's one way to think of this model. And that's not reality, but it's one way to describe how the van der Waals forces arise. So then you have another atom, and it needs to be close, right? And you have an electron around that atom, and it's also circling around in its orbit. So the close means talking about angstroms, right? You need to be less than a nanometer for sure. So you need to have two things that are in close contact, intimate contact, we can say. And when they're close enough, and I'll show you the reason for that, there's a reason for it, and I'll tell you about that. So when you have two atoms and they get close like this, you can imagine that at some point in time, you have the two atom nuclei are here, right? And this electron might be in this position, and this electron on this atom might be in this position. When this happens, this electron is attracted to that nucleus, right? Because it's not shielded. So that, and conversely, right? This is going to happen some of the time. Now, the logical thing to think is, well, okay, but you're also going to have, can you see that? Oh, that's terrible. These are terrible. You're also going to have a situation where the electrons are like this, right? I'm really butchering my art here. I'm trying to keep it on the page. And so then the electrons are going to repel each other. It should all average out, right? It should all average out to zero. But that's not what happens. What happens is electrons are both particles and waves. So when people talk about atoms, they talk about electron clouds. And what happens is when you get two atoms together, and this is any atom, right? It doesn't matter what kind of anything on the periodic table, any atoms, when they get two together, whether they're like, unlike, whatever, that what happens is those electron clouds will deform. They will deform according to certain principles, and I'll show you what those are in just a minute, right, on the slide. And and the net results is you have attraction, and that attraction is called van der Waals. Right? So so these are am I on screen here? So what this results in is called transient dipoles. Because when you have a, so what a dipole is when you have a two atom, when you have a molecule, and the classic example is hydrogen chloride, not hydrochloric acid, but hydrogen chloride gas. You have a hydrogen atom, and you have a chloride atom, right? So because of electronegativity, what's going to happen to the electron cloud is it's going to go like this, all right? The chlorine is stronger and pulls electrons, it wants electrons. If you remember your chemistry, right? Chlorine is 1 electron short of having a full shell and a more stable, lower energy environment. Hydrogen is number 1, right? So what happens when you have hydrogen chloride, or when you have 2 different kinds of atoms, they will pull, the electron cloud will get pulled, and you'll have, chemists write it like this: delta plus on the hydrogen and delta minus on the chloride. And so this will give you a dipole. If you draw it from minus to plus, that's just convention, right? There's nothing fundamental about that. So this will give you a dipole, which means, I'm still on the, separated charges, right? So when you have a dipole, you have charges that are separated, and when you have 2 different charges, a plus and a minus, you've got voltage and all that kind of stuff, right? So you have, when you have van der Waals forces though, so this, with hydrogen chloride, you have a permanent dipole. With van der Waals forces and surface attachments and things like that, and you have 2 atoms that are close to each other, hydrogen, hydrogen, carbon, carbon, whatever, so that the electronegativity is not an issue. You still will have a dipole, but it will be transient, right? It will exist for, I don't know, tiny, tiny, tiny amount of time, maybe attoseconds or something like that. And as the electron cloud fluctuates, and so the that will give rise then to van der Waals forces. Okay. This takes time. So van der Waals forces. So here's a chart of the different types of forces between molecules, right, or atoms. It's not everything, but it's the things you encounter most often. So first of all, you can have a covalent or a metallic bond up here at the top. And here, as you remember from chemistry, with a covalent bond, you have overlapping orbitals. And a good example is ethane here, CH3CH3. So you have sp4 bonding, right? And then you get you get a single bond, and the electron clouds merge, and so the electrons can circle around. If you want to think of it back using that same analogy, instead of a wave, you can think of a particle, and the particles are orbiting both of the nuclei, right? And then that's a bond. That's a covalent bond. Then you can have a charge-charge bond called an ionic bond. Example is salt, sodium chloride. So you have sodium plus Cl minus, and you have plus charges and minus charges. That's an ionic bond. These two, covalent bonds and ionic bonds, are called primary bonds, right? So where's my... So these are called, get out of the way. So covalent and ionic bonds are called primary bonds. All the rest of these are called secondary bonds. Right? So the van der Waals forces come from secondary bonds, not primary bonds. Primary bonds are much, much stronger than secondary bonds. I've got a chart later on that will give you some numbers for that. Okay, so And there's a lot of different ways that molecules or atoms can interact. So here you have charged dipole, 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 charged nonpolar, dipole, nonpolar, two nonpolars, and then hydrogen bonds. Hydrogen bonds are a special case. We're going to talk about those. So notice though, the R here is the distance between the atoms, right? So, and it applies to molecules too. So R is the distance between the atoms, and these different forces between molecules and atoms have different distance dependencies, right? So this one's R squared, R to the fourth, R to the 3, R to the 6, R to the fourth, blah, 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 right? So, the ones that are R to the 6th are called van der Waals forces. That's the definition, right? And there he is, Herr Dr. Professor van der Waals. Long time ago, more than 100 years, I think. I'm pretty sure about that. So when the distance dependence is 1 over R to the 6th, we call it a van der Waals force. Okay. Yeah. Oh yeah. I left out I used to give an equation. So that the van der Waals forces arise from, as maybe you've already, I have a feeling for this. They arise from how that we were talking about transient dipoles and the electron clouds deforming. So you can imagine that the tendency to form van der Waals bonds depends upon how easy it is to deform those clouds, how strongly the electron clouds are connected to the nucleus of their atom, and how easily they can feel the nucleus of another atom, or the deformed electron cloud of another atom. Right. So there's it's not really quantum. It's electrostatics, basically. Well, I guess it's electrostatics on a quantum level. So,
Professor,
yeah.
could I ask a question?
Of course.
So is this force then dependent? It's been a while since chem. Dependent on like which side of the periodic table it is for electronegativity. So if we're like leaning farther to the right, the van der Waals won't be as strong or likely to form bonds is the left-hand side.
Vaguely, right? Vaguely. It's not directly. In the equation for van der Waals, as I recall, it's ionization potential and polarizability. So and I don't think electronegativity you might be able to relate those, but it's not really in the equation for van der Waals forces. I think that's right. Okay. But electronegativity turns out to be really important, and we're going to talk about that. It has more to do, electronegativity is really critical when it comes to hydrogen bonds. So we're going to discuss that.
Okay, great. Thank you, Professor.
Yeah. So van der Waals forces are often almost modeled using the Lennard-Jones potential energy equation. This is the equation. So in chemistry, by convention, there's nothing fundamental about it. By convention, we say that attractive forces are negative. They tend to lower the energy, they tend to draw things together, we call it negative. And repulsive forces are positive. So you have a attractive force term here and a repulsive force term here. So when you plot these two curves together, so you add those, you sum these two, what you get is something that looks like this. So R to the 6th is much different than R to the 12th, right? So again, R to the 6th is the van der Waals attractive force. R to the 12th is the repulsive force of basically the two atoms are hitting each other now, right? The nuclei are getting too close. And so you get nuclear repulsion, nucleus repulsion. It's not like a brick wall. It's, but I mean, it's close, right? Arc the 12th is close to being just going to infinity in no time. So the attractive force operates at longer distances than the repulsive force. So here you have, once you're far enough away, the R to the 6th and R to the 12th just wash out the A and the B, and you have no force at all, right? So you have to be close. And then when you get, as you keep getting closer, the adhesive force or the van der Waals force keeps getting stronger, but at some point the R to the 12th starts to take over, and when it does, it goes up to basically infinity. So Lennard-Jones potential. In your homework, which I apologize for not getting it up, it should be up already. So I will get it up. I may make it shorter than usual, and I'll get it up today. But it has a question about this, because this is the fundamental chemistry and physics of how adhesives work. Because the adhesion theory, number 5, is the most important one. It's the most important for wood, and it's the most important for everything that you glue together. And understanding the fundamentals of how it works, to me, is really important. That's what I'm trying to teach you. So you've got a question on this on your homework. And there will be a question on this on the exam. And here's a video.
I'm Al Crosby. I'm Doug Kershik. We're the GEXSkin team.
The GEXSkin team, Crosby, Kershik, Andrew Cole, and doctoral students Mike Bartlett and Ian King, here at the University of Massachusetts Amherst, have invented a revolutionary new adhesive device made of simple, inexpensive material that can hold up to 700 pounds on a smooth surface. It's based on some key anatomical properties of the gecko foot, which is covered with millions of little hairs called setae. Crosby and his group hypothesized that the setae alone are not the only feature allowing a gecko to adhere to walls. They suggested that a stiff tendon directly integrated into the skin is also critical.
So these are the properties that we've been trying to work on, are really high capacity, easy release.
And these geckos have done that by making millions of little hairs, which are so small that they can get very close contact with the surface, and that provides force they need to climb. But our contribution that Al and I have really worked on, along with Mike Bartlett and King and other people, is to really look at actually the whole organism, to look at not just the hairs, but also to look at the underlying anatomy, look at the tendons and soft tissue, the skin that underlie the structure, because it really is a whole foot, not just the hairs.
The key innovation by the GEXSkin team was to create an integrated adhesive with a soft pad woven into a stiff fabric. This allows the pad to drape over a surface to maximize contact. Further, as in natural gecko, the fabric is woven into a synthetic tendon, yielding a design that maintains stiffness and rotational freedom using everyday material.
And what it does is it just drapes easily over the surface, gets close enough that the van der Waals interactions can become strong, and it can hold, 700 pounds, maybe on an index card size pad, but then with a simple, twist of the pad, it peels off with zero force, and it doesn't mark the surface at all. And one of the really important things is that you can do this over and over and over again.
What's unique about GEXSkin is the kind of use of very simple materials in a very novel way.
GEXSkin opens up new opportunities for adhesion that we never envisioned.
Okay, so that's van der Waals, right? They're using van der Waals forces to make an adhesive, and only van der Waals forces. And of course, there's this video is a number of years old now. There's all kinds of van der Waals forces adhesives out there now. They work underwater. They use them in outer space. They're all over the place. They've got limitations, like what happens when your van der Waals adhesive pad gets dirty, right? So there's some operational limitations and stuff like that, but in terms of fundamental science, it's really, I think, really interesting. And one thing, a lot of this, a lot of this work has been funded by the military because they're interested in having soldiers do stuff like this. Although they'd rather have them do it as fast as Spider-Man, right? So going right up the glass, leaves no marks. It's easy to remove, so you want to be careful about which one you remove, right? Things like that. And there's some physics involved in where is the weight, how's the weight distributed, and things like that. Right? Okay. So, van der Waals forces. Now let's talk about hydrogen bonding. So hydrogen bonding, hydrogen bonding is critical to life. Right? Hydrogen bonding is what gives water its special properties. And we talked about hydrogen chloride, but here you can see hydrogen bonding between two water molecules. So again, remember we talked about dipoles. So here's your partial plus charge, your partial minus charge. And in water molecules, that's what you have. This is because of the difference in electronegativity. Tiana. So the difference in electronegativity gives rise to these dipoles, and they're not transient, right? They move around, but they're not transient like van der Waals. They're permanent dipoles. And then you have, so that the hydrogen can then be attracted to the delta plus on the hydrogen is attracted to the delta minus on the oxygen. So you have lots of hydrogen bonding in water. That's why water with a molecular weight of 18 is a liquid. If you have something that even like, well, if you have methane, molecular weight of 16, it's a gas, right? If you have ethene or ethane, molecular weight of 30, still a gas, right? It's the hydrogen bonding that holds the water molecules together that gives it the high boiling point that it has, that makes it a liquid over a range, but also has a low molecular weight, so it has low viscosity. So also, hydrogen bonding is what holds cellulose together, right? Cellulose is made up of glucose, right? And glucose is a type of sugar, and it dissolves in water. So why doesn't cellulose dissolve in water? Because of hydrogen bonding. It's the only reason. If it wasn't for the hydrogen bonding, cellulose would dissolve in water. But because you've got hydrogen bonds, and because you've got lots of them, right, as you can see here, the dotted lines here are all hydrogen bonds. So there's a lot of them in cellulose, and they really hold the cellulose together. That's what makes the cellulose crystal, right? And even in amorphous cellulose, you're going to have hydrogen bonding between two cellulose molecules that's going to affect the properties. So we have here's the periodic table, and the electronegativity goes up and right, if you remember that from chemistry. So the highest electronegativity is fluorine. I think that's here. Fluorine is 4.0, really strong, and then it drops rapidly from there, right? So you have, and as it says up here, you really only get hydrogen bonding in the situations that we're interested in wood adhesion. Hydrogen bonding is only important with nitrogen and oxygen. fluorine forms a hydrogen bond, but it's too strong, right? Makes a really strong bond. And so hydrogen bonding in fluorine is really different than hydrogen bonding in oxygen and nitrogen. And that's why you have lots of fluorine in Teflon, but Teflon is not sticky at all. And it's because of the strength of the fluorine bond, right? And so also you see that chlorine has electronegativity that's the same as nitrogen. Why doesn't chlorine form strong hydrogen bonds with wood? The reason is you're one row down in the periodic table, and chlorine is a whole lot bigger than nitrogen. So it's too large to form a good hydrogen bond. In order for the hydrogen to be, the hydrogen's looking for the stronger, the more concentrated the charge is, right, the stronger the bonding is going to be, because you need charge versus charge divided by distance. So the nitrogen and the oxygen are small molecules compared to the ones below them, right? And and there's also a lot of them. There's also a lot of, especially oxygen in wood, but there's also nitrogen. There's nitrogen in proteins, DNA, RNA, et cetera, et cetera. So nitrogen and oxygen are abundant in organic materials, typically, especially renewable materials. And so hydrogen bonding is pretty much only important when you have nitrogen and oxygen around, which we have plenty of oxygen in wood. This does not mean that there is no hydrogen bonding between other elements. There is. It's just a lot weaker, right? You can have a CH bond and another CH bond and get hydrogen bonding between the hydrogen and the carbon. It's just a lot weaker, that's all. And so the hydrogen bonds that are strong enough to make a difference in wood and in wood adhesion are with nitrogen and oxygen. And we don't worry about fluorine. It's too strong. It's kind of a special case. It acts weird. Its behavior is weird, right? Everything else below this row is too big to give you a good hydrogen bond, and everything to the left is too weak. So nitrogen and oxygen. Now, the reason that hydrogen bonding works so well is because it's number one on the periodic table, right? There's only one number one, and hydrogen is it. So it is, and the thing of it is when you have hydrogen, you have one proton and you have one electron. So hopefully everybody remembers that. It's number one, and the one means you have atomic mass, or you have an atomic charge of one, right? So you have one proton and one electron. When you make H plus, it means you remove the electron. And hydrogen is the only atom in the periodic table where when you remove the one electron, you remove all of the electrons. Every other atom, when you remove an electron, there's still electrons left. So you have an electron cloud. That you're just deforming the electron cloud, right? For every other atom. But with hydrogen, when you remove the electron, you eliminate the electron cloud. This means that the proton diameter is 0.02 picometers. Picometer is 10 to minus 12. For example, a carbon atom is 182, right? So the difference here in size is 10,000. So the proton is 10,000 times smaller than a typical carbon atom. That means that the proton can fit into spaces that all the other atoms, especially carbon, cannot. So it can move freely through organic matter, depending upon where it's attracted and where it's repelled. Right? Also, the carbon mass is about 12, hydrogen mass is 1, right? If you just do a simple estimate of kinetic energy here, the velocity of hydrogen compared to carbon is 3 times faster. So when carbon can move a little bit, hydrogen can move 3.5 times as far. So hydrogen can zoom around in any kind of a molecule, fit into tiny spaces, and form hydrogen bonds. That's what makes hydrogen so special and why hydrogen bonding happens only with hydrogen. So hydrogen bonding is responsible for DNA. So you have a double helix, and the double helix is formed out of hydrogen bonds. Right? That's what makes the double helix form. And you have water, ethanol, alcohols, they all have hydrogen bonds. And this is a video. This is a molecular model of water.
An intricate molecular dance is underway. The loose, sensitive network of hydrogen bonds holding water molecules together is forever shifting, with each molecule continually switching dance partners. This simulation, created by chemical physicist Michael O'Deely at Stockholm University, reveals just how intricate the dance of water molecules can be. The hydrogen bonds break and then reform with an angular jump of about 50 degrees. And it turns out the molecules switch dance partners at a dizzying pace, about once every 6 picoseconds. That comes to about 160 billion times a second. This work helps researchers thoroughly understand water, the stuff that makes up more than half our bodies and covers 70% of the Earth's surface.
Okay, so that video doesn't really give you, if it was switching 160 billion times a second, it would be hard to watch, right? So that is slowed way down. And there was more things in there were green and blue and stuff. There's more things in there than just water. Must have been dirty water or something. And but it gives you some idea of what hydrogen bonds look like in simulated real life. Okay, how does all this affect us here in real life, macro-sized? So if you have a nonpolar compound, for example, ethane, here's the formula, CH3CH3, molecular weight's about 30. There's no dipole moment, right? There's only van der Waals. Remember, van der Waals is transient dipoles, not dipoles. So you have that 1/r to the 6th dependence. You always have that. That's always present. And sometimes if you, I don't know, if you get into this, people may tell you that you can have negative van der Waals forces, but that's not really true. You only have, the only way you can, if you have 3 different phases, like oil and water and air, you can have a situation where it appears that there are negative van der Waals forces, right? So oil spreads out on water, but water beads up on oil, but it's because air is hydrophobic, right? Water is hydrophilic. So you can describe that as negative van der Waals forces, but it's because there's 3 phases. When you only have 2 materials, there's always an attractive force. So we live in a universe where everything attracts everything else. And isn't that nice? Right? Okay, so the boiling point here, which is a measure of the cohesive forces between the molecules, right? The stronger the bond, the stronger the forces between the molecules, the higher the boiling point. So when you only have van der Waals, you have another word for in this situation where you have nonpolar, have 2 nonpolar molecules and the force between those. You'll also hear that called London dispersion forces. Right? So, but it's one, that's a type of van der Waals force. And you have a boiling point here, minus 89. Formaldehyde, same molecular weight, but it's got a dipole moment, so it's polar, right? And that the boiling point goes up, what, 68 degrees, something like that. So that's like enormous. Now you have methanol, 32, almost the same molecular weight. You have a dipole moment, but it's weaker, but you have hydrogen bonding. Now, hydrogen bonding brings the boiling point up to 64. So again, you've got an enormous increase here. And these are other examples, and they do the same thing. So it's not just these particular molecules. Nothing magic about those. What's magic is difference between nonpolar, polar, and hydrogen bonded. Okay. Again, if you've got questions on this, please, I mean, this is hardcore chemistry, so if you've got questions, let me know. Some examples of bond strengths. So we talked about ionic bond, primary bonds and secondary bonds. Covalent bonds are primary bonds. So a carbon-carbon bond is this number. Carbon-nitrogen bond is this number. Carbon-oxygen, this number. Carbon-hydrogen, this number. And for ionic bonds, it follows this equation, right? So it's the distance. Now, I probably should have made that an R, but this is the distance between the atoms. Charge on one atom, charge on another atom. This is the Faraday equation for electricity, right? If you have two different charges and they're opposite sign, you're going to have one's minus, one's plus. This is going to be a negative number, right? And it disperses, the force reduces as the square of the distance between the forces. And then you have a K to get the units right? And this is force then. So that's what ionic bonds are. It gets a lot more complicated than that, of course, when you get into real life with solvent molecules and all that kind of stuff. But in just isolated point charge atoms, that's what it is. Typically, these can be in the neighborhood of 200 so they're smaller than covalent bonds, but still reasonably strong. When you get to hydrogen bonds, again, fluorine's a special case. You get these enormous hydrogen bond strengths, but they're actually too strong, right? It's more like a chemical bond. And so you do get hydrogen bonding with fluorine, but it's not, it's different, and it doesn't really behave the way the other hydrogen bonding atoms do, oxygen and nitrogen. So here you have oxygen, hydrogen, nitrogen, right? And here you have a strength of 29 kilojoules per mole. Here you have oxygen, hydrogen, oxygen, and a hydrogen bonding strength of 21. This is important. The nitrogen, oxygen, this could be a hydroxyl group on cellulose or lignin or hemicellulose, right? And this is nitrogen, and this hydrogen bond is stronger than the hydrogen bond between the same hydroxyl group in wood and oxygen, for example, water. So if you have a nitrogen-based compound and put it into wood, it displaces the water. And it will also displace the hydrogen bond between, for example, cellulose molecules. So this is one reason that some people, some companies use ammonia to deconstruct wood before they make biofuels, right? If you recall, when you trying to make cellulosic biofuels, you when you're trying to make cellulosic biofuels, you need a preliminary step, and that preliminary step is often hydrogen or sulfuric acid, but you can also use ammonia, and the ammonia then ammonium hydroxide solution, right? Ammonia and water, and that will be effective as well. And it's because of this. It's because of these numbers, right? So, okay. And then van der Waals bonds are way down here, 2 to 5. However, you have to remember the multiplier, right? To get these bonds, you have to have an oxygen atom and a nitrogen atom in close proximity. Or an oxygen and an oxygen in close proximity. That doesn't happen nearly as often as every atom in close proximity to every other atom, right, that it's in proximity to. So there's a huge multiplier on the van der Waals bonds. And it turns out that if you do the math, the total sum of the van der Waals bonds is much greater usually than the sum of the hydrogen bonds. Not always the case, of course, and the hydrogen bonds are important. So when we want to make an adhesive to get a high adhesive bond strength to glue our wood together, we want hydrogen bonds, but we've got to have van der Waals bonds too. So, and I probably misspoke. There are cases where the hydrogen bonding plays a bigger role than the van der Waals, but there's a lot of cases where the van der Waals plays a more important role than the hydrogen bonding. Okay. So now the next thing we need to talk about is surface tension. And for this, I need to go back to my pad. So imagine that you're a molecule. So I'm just going to draw a circle for a molecule. That's better. And this molecule in a liquid, it could be water, gasoline, alcohol, whatever, all right, glycerin. So this molecule is surrounded by other molecules. My molecules are not all the same size, I know, but hopefully this will illustrate what's going on. Okay, so let's pick a molecule. I'll pick this one, and I'll change colors since I have my color pad here. First of all, this thing would not be, as I mentioned before, this thing would not be a liquid if there weren't forces between the molecules, right? If there are no forces between the molecules, then it's going to be a gas. There's nothing to hold it together. Those forces are called cohesive forces. So it's the force that holds the molecule together, or it holds the liquid together, right? The forces between molecules. And you also have temperature, which is movement of molecules, right? Or atoms or whatever it is. So the movement is generally the thermal background that we live in is described scientifically by a number on a molecular scale called KT. On a macro scale is RT. R is the ideal gas constant, K is the Boltzmann constant, and K times Avogadro's number is R. So you have going from atom to mole. So we're interested here when talking about atom to atom, talking about KT. So when you have enough thermal energy, when KT is high enough, when KT exceeds the cohesive energy between the molecules, whether it's only van der Waals is always there, right? Exceeds van der Waals or exceeds van der Waals plus dipoles from the polarity in the molecule, or it exceeds hydrogen bonding also, then the molecules will be set free and the liquid will boil and will turn to a gas because now the thermal energy is greater than the cohesive energy. Hope everybody understands that. If you don't, then let me know. All right, we'll talk about it further. Okay, so we've got forces between these molecules because they're a liquid. So we know that. So what are the forces? If we look at this one, well, there's going to be a force here, force here, force here, force here, force here, force here, force here. And if we sum those forces over time and space, they're going to equal 0. Right? But now let's look at what other forces when you're on the surface. So up here is air, right? And down here is the liquid. So if you're on the surface, and I'll pick this guy, then you can go, you have a force here, force here, force here, force here, force here. And if you sum these forces, they do not equal 0. Right? You see that? So what you're going to get, if you sum all of these, take all of these arrows as vectors and you sum them all, what you're going to get is a force that goes directly down into the liquid. The density of the liquid is 1,000 times the density of the air. So the air is basically a tiny, tiny perturbation on the whole system. There's going to be, you can have forces between the surface molecules and the air, of course, but it's tiny, tiny compared to the forces between the molecule on the surface and the liquid. So that gives you then a net force, and that net force pushes straight down into the liquid. So things, and people have done experiments, and they have shown that the density on the surface is a little bit, let that ring please. The density on the surface is a little bit greater than it is in the bulk, right? Because these molecules are pressing down, the surface is pressing down on the molecules underneath, right? So you get a higher density, but it also, the very surface, they tend to spread out a little bit, right? Because they're being pulled down into the surface. So, but they're pushing on the ones below. So that gives rise to what we call surface tension. And we go back now to this. We'll go back to the PowerPoint now. Okay, so this is the same thing. So here you have a bulk molecule, a surface molecule, right? And you have a surface, and it could be, for example, a liquid that's a drop on a piece of wood or piece of concrete or whatever, steel. So this is repeating what I've already said. So you have this on your PowerPoints. And this force is called surface energy or surface tension, right? When it's a liquid, when you have a liquid and air on a solid, it's usually called surface tension. But everything has surface energy, right? There's surface energy between, every time you have a surface, you have surface energy, okay? And the, let me see if I can write it. Oh, it's so much easier in class. I'm gonna have to do this. Thermodynamically, you have surface energy is almost always symbolized by gamma, and the thermodynamic that didn't work out so well. So you have surface energy. The thermodynamic definition is the free energy. The partial differential of the free energy is a function of area. Right? So it's free energy divided by area. And that's surface energy. And that's almost always is going to be called gamma. This, if you want to get specific is. Right. You remember your thermo, that's constant temperature and pressure. So that's the thermodynamic definition of surface energy. And here's some, so I write so slow with the mouse. Hopefully everybody's got that already. So let me clear it. And here's some videos.
I'm your host, Vince Whitman. Hey, want to see something really cool? Check this out. Yep, that's a paperclip. And it's not sinking. But wait, how is that possible? The paperclip will dense in water. And we know that if the density of an object is greater than the density of water, the object will sink, right? So why is the paperclip floating? This demo works because of a property known as surface tension. And surface tension is also responsible for a pretty cool trick for sticking in space. Here's Canadian space agency astronaut Bob first to explain what exactly surface tension is.
Molecules at the surface of a liquid experience unbalanced molecular forces. Since they are on the boundary, the molecules are attracted from inside, but not from the outside. This causes the surface to behave like a stretched elastic membrane. Life on the Earth is dominated by gravity. Think of the things you use every day. You ride in a car, you eat with a spoon, sit in a chair, you drink out of a cup. All of these things inherently depend on gravity. But up here in orbit, the effects of gravity seem to disappear. With gravity out of the picture, other forces start to dominate our daily work. One such force that becomes very important here in orbit is surface tension. Here in space, surface tension is critically important, even for something as simple as getting a drink of water. If I poured out this drink of water on the Earth, gravity would smush it flat. But here in orbit, it floats in midair. It makes a perfect sphere.
So you can see that there's a lot more going on with surface tension than sinking or floating. And it's easier to see those perfect spheres of water in space.
Okay. So you measure surface tension by using an instrument. We have one. It's in chemical engineering here on campus. And so when you measure surface tension, you can do it by putting a drop on a surface. And as you can see, that drop will spread out until it comes to some kind of equilibrium. And that equilibrium then will have an angle. And you'll have an angle between the surface and the liquid, right? And there it is, right? So you can see this angle here, and that angle is almost always called theta, right? And that's the contact angle. So hopefully you've heard about that. So you can always, so you'll have a contact angle between the liquid, where the contact angle that the liquid makes when it's sitting on a surface. Right? This is not a hole, this is a reflection. Right? You need some light to take the video. So there's theta, that's the contact angle. And nature also uses surface tension. Okay. So surface tension is all over the place, and it plays an important role in daily life. And one of my favorite stories about surface tension comes from Einstein. He and a friend were walking on the beach, and the friend said, "Dr. Einstein," I don't know, maybe called him Albert, "how come when we walk on dry sand, it's hard to walk, and when we walk on wet sand, it's easy to walk?" And Dr. Einstein said, It's obvious, my friend. Surface tension. So surface tension is the water between the sand particles, right? And it holds them together, and you also have some hydrogen bonding going on there, right? But you're walking on, when you have walking on wet sand, you're walking on surface tension. So that wasn't obvious to me, but it was obvious to Einstein. So now you have something to baffle your friends with, that and we can all start going to parties again. Okay. So those are the fundamental forces that are involved in adhesion. And we've covered the 5 different theories of adhesion. We spent a lot of time on, whoops. Oh, man. And we spent a lot of time on the adsorption theory of adhesion. And that's because it's really important. So I'm out of time, unfortunately. And we'll have to take this up again next week on Tuesday. I don't even think we're not gonna get to the last lecture, unfortunately. If you want me to talk about nanocellulose and wood plastic composites instead of CLT, then let me know, because a lot of you are CLT experts. You probably know more than I do. So, but we're gonna have to cut something. This doing it remotely takes a whole lot more time than doing it live. So let me know, have a look at the syllabus, let me know what you'd like to cut, and we will discuss it perhaps on Tuesday. But we need to finish this part, because this is really critical fundamental knowledge to wood science of how glue works and why we use it on wood.
Professor, could I ask a quick
Yeah.
question?
Sure.
So it says on the schedule that there's an exam next Thursday, or it says revert to standard time. Does that mean we could potentially take the exam during our scheduled final time?
Yeah, but the only issue with that, it's fine with me. Whenever you want to take the exam is okay with me, not a problem. The only issue I see is that in order for you to take you can take the exam once I publish it on Canvas, right?
Mm-hmm.
And when I publish it, it publishes for everybody. So we really can't have some people taking the exam on Thursday and other people taking the exam. It's okay.
Sorry.
Okay.
Sorry, my dog jumped off the porch to chase a kid on a bike down the street. Sorry, go on.
That's all right. So everybody needs to take the exam at the same time.
Mm-hmm.
I think that's the case. Is that you folks know more about Canvas than I do. Have you had other class? Usually we give the exam in class, and we usually do it on Thursday in lieu of a laboratory. So don't see much point in a lab on the last day of class when you can't write a lab report or anything. So
then my question would be, will the lab 7 be due the day of the exam?
No, if you would like, we can make it due. I don't want to go too far. We can make it due the day that the final is supposed to be, right?
Okay.
And we can do that for, if you want, it's okay with me. We can do that for homework too, because we're getting a late start on homework. So why don't we make the homework and the lab due when you would be taking the final and take the exam on Thursday? Or would you like to do it, if you want to do it the other way around, we can do that too.
I would think that'd be a great question to ask the class, because I know like Mohit and I have a presentation, like our like final project presentation right before the scheduled exam time. And what I'm personally afraid of is not having enough time to study, because I have 2 final presentations next week.
Okay.
And so with that, a lab and a homework, I don't see how I could like possibly do well on an exam with assignments too.
Right.
But I'm sure the rest of the class has preference on whether they'd have the homework delayed or the exam delayed. So I'll leave that to them.
Okay, and I need to find out when you take an exam on Canvas, if you can take it whenever you want, and you just get, you get a certain amount of, I know the questions are timed, or they can be timed. So I assume the quiz is timed, but it doesn't make, you wouldn't, but I think everybody has to take it at the same time. So.
I know you can set it to be open for like a window. So you could say that it's this day, and then anyone can start it at any point during that window you set, and then you can also give it a timer separately.
Okay. All right. So, well, I'll send an email, and you can respond and let me know what you'd like to do, and we'll get it figured out. But yeah, there's nothing written in stone about when we take the exam or when the homework and the lab reports are due. And I'm feeling guilty about not getting the homework to you on time. So I would like to give you more time to do the homework. So we could do something like have the lab report and the homework due on Monday, and then whenever we're supposed to take the exam, if it's not, well, we can just make it whenever we want during finals week, right? So let me know a good day for you, and I'll send an email to everybody, and you can respond. Let me know a good day for you to take probably a couple of days that would work for you to take the final, and when you would like to have the lab report and the homework due. Okay. Awesome. And I'll get you I'll make sure I think there's already a practice exam, so you can get a clue about my style, and I will get I'll get your homework. Your homework 1 is graded. I just have to get it to you. So doing it remotely is a lot harder than sticking it in your mailbox. So I will get it to you hopefully today. Well, I'll just make it a priority to get it to you today. So you have some, everybody did well on the homework, so it's not a problem. The only thing that people, I didn't go over it in class because there's some people that haven't handed in the homework yet. So about the only thing that the people missed on was on the treatment problem. You only treat the sapwood, and they didn't account for that. So other than that, it was pretty much good. So anything else?
I have a question, sir.
Yeah.
So I wanted to know, we are still not like getting to see the videos on Canvas, like for class lectures. Like I would really want to rewatch today's class lectures.
The recordings the recordings are, go to YouTube and my channel, John Simonson channel on YouTube, and watch the recordings there. Okay.
Okay, sir. Thank you.
Instead of on Canvas.
Okay.
On Canvas, Canvas screws them up. I couldn't. They're not working right on Canvas, but YouTube's pretty straightforward. Yeah.
Okay, sir.
So all the lectures and all the labs should be on YouTube. And there's, if you look under labs, if you go to the files on Canvas under labs, there's a Word document there that gives you direct links. So you can also get to it that way. Right. So you've got 2 different ways to access it. But accessing it on Canvas is, I don't understand. Well, my skill level is so low on this. So it says, when you put up a video on Canvas and you try to publish it, it won't let me publish it to the class. It lists every class that I teach except this one. So I don't know how to make that work. I haven't figured it out. So yeah, and I think Dr. Nairn had the same issue because a lot of his videos are also on YouTube. So anyway, anything else?
I have a question regarding the lab report for today.
Yeah.
The biogas generated in the pyrolysis have the same composition of the syngas, the gas generated by gasification, or are
No, I
different?
don't. No, it doesn't. No, it's the biogas in pyrolysis is simply the low molecular weight compounds. So they burn pretty well, but there are things like acetic acid, methanol, and you probably do get some syngas. You probably do get some carbon monoxide and some hydrogen, but because it's at a lower temperature, mostly what you're getting is volatilization of degradation products from the wood. And some of those are low enough molecular weight that they're gases at room temperature. But it's a mixture of different compounds. It's not just CO and H2. And so gasification kind of at those higher temperatures and with the catalyst that they use, it breaks down the molecules into those simple molecules that give you syngas.
Thank you. And my other question is, what do you expect in the discussion? Compare the result to other research or?
Well, not so. For lab reports, the template is fairly elaborate. That doesn't mean that you have to write a lot. Right? You just have to write what you did in the lab and make sense of it, explain it. You don't have to just write on and on and on. So discussion doesn't really have to be all that detailed, but you do have to cover what went on and why, right? So the important thing we're trying to do here, the thing that I'm trying to do is to get you to use critical thinking and to understand the fundamentals of what's happening. So if you know the fundamentals, then you are well positioned to go in any kind of direction you want to go once you get out of here, right, and start living your real life. And so understanding the fundamentals of wood science and the fundamentals of what we do in the lab, that's what's important to me. And also demonstrating that you can think critically about what we do. Those are the things that are, most important for me.
I do have another quick question, so sorry.
Sure.
This might sound like a stupid question. Like the gases from the receiving container, do we necessarily have to flare them, or can they just be left to just burn out or escape rather?
Well, no, I flare them because I think it makes for a better lab. But no, you could run them into a internal combustion engine and turn them into mechanical motion, right? So that's what the video, well, the video didn't work about the Swedish students making a car. But yeah, you can take the gases from pyrolysis and you can do lots of things with them. You can collect them and then make various kinds of bioproducts or biochemicals out of them. Or you can use them as a fuel. You can store them. You can dissolve them in a solvent. So store them that way. So there's a lot of things that you could do with those things besides flaring them. It's just that in the lab that I did, that hopefully I wish you would have been there to do it, but in the lab, it was just easiest to flare it. Plus, it gives you I think a better demonstration that you actually do have biogas. Yeah. And you see that and you only got the flare in the beginning, right? As it went on, the flare died down and eventually went out. And that's because as the temperature got higher, you broke down larger molecules into pieces that weren't volatile. So they condensed and came across as bio oil. They weren't gases at room temperature. But in the beginning, then you're going to get these volatile compounds that come across as biogas. And when you're doing this industrially, you can tune the system so you can produce more biogas, less bio oil. But most of the time, people try to tune their process so that they optimize or maximize the bio oil, right? Does that answer your question, Kenneth?
Yes, it does. Thank you very much.
Okay. Anything else? All right, then next time we'll talk about polymers and finish up talking about glue, and we'll move on to composites, unless I hear differently that people would rather hear about nanocellulose and wood plastic composites. And as we could switch it around, well, yeah, there's just not going to be any time. We're going to lose a whole lecture one way or the other. So if you have some preferences, let me know, and I'll send an email about due dates, okay, and final exam dates. Is that it? Okay, so everybody have a good Thursday, and I will see you next Tuesday, if not sooner. Be well.
Thank you, Professor.
Yep, bye-bye.